So next part of the problem is a platform weight W 4000 pound is being supported by a It is estimated that the damping in the structure is of order 5% of the critical damping. Determine for this structure the following. Element and the number of cycles and the time required for the amplitude of the motion to be reduced from an initial value of 0.1 inch to 0.01 inch. So in this problem, there is a platform which is supported on the four some net issue is there, so maybe there is some problem. So this problem we were doing. And there is a 4 columns. So we can determine the stiffness by F over delta, and from that we can determine the natural frequency by K into G over W. W is given the weight of this platform. आवाज आ रही है?
जी सर आ रही.
We can compute the omega, and then the critical damping, the formula that we proved today, 2 under root km. So 2 into k into m is W over G. M is W over G. That comes out to be, this is the critical damping. From that, the absolute damping can be computed by the zeta into CCR, because CCR is the ratio of the C over zeta. So the absolute damping C can be computed because that is given. The damping ratio is given. That is the ratio of the C over CCR, damping ratio. So damping ratio is 5% into you multiplied with the CCR to get the value of the absolute damping. Now we can compute the logarithmic decrement, because the question is that logarithmic decrement, how much is the successive amplitude ratio, delta. So delta is log of the first vibration to the next vibration. So that is equal to the, let's say 2 pi zeta minus 2 pi the next one minus this one. So these are the different values of the decrement. So u0 over u1 can be determined, because the first decrement is u0 over u1, that is equal to 1.37. This is the ratio of the successive decrements, because it is given that the number of cycles and the time required for the amplitude of the motion to reduce from the initial value of 0.1 to 0.01 inches. So let's say the first value is 0.1 inches, and we have to see that how much numbers are needed. So you can use alternatively this formula also, are the one which I used in the last example, and you can compute the number of cycles by this way or that way also. That log of this over this should be equal to the 0.314. That value is comes out to be the zeta over 1 minus zeta square. And the damped frequency is given by the omega into 1 minus zeta squared. So these values are given, and we can compute the damped frequency. And the damped time period is 2 pi over omega t, because time period is 2 pi over omega n. That is the natural time period. And when you have to use the damped time period for the damped system, that is 2 pi over omega t. Then the time for the 8 cycle. So if there are the 8 cycles, the time period will be the 8 time the TD. So that comes out to be 1.62 seconds. In this problem also, a cable is supported, a heavy cable table is supported by the flat steel legs. It's a problem from the book. Its natural period is lateral vibration is 0.5 second when this plate is clamped to its surface. 50 pound. The natural period of the lateral vibration is 0.7 second. This is when it is 50 pound plate is clamped, and this is unknown. What is the weight and effective lateral stiffness of the table? The natural period in the lateral vibration is lengthened to 0.5 seconds, 75 seconds in this case. In this case, 0.5 seconds. So we can we know that the damped period of vibration, in this case the damping is same, so you can just write the equation for the Tn 2 pi under root m over k. And so this problem is not different. Actually, I can send you the solution. One equation you will make with the time period with the, you know, that is 2 pi into m over k. So Tn is 0.5 is given, and m is 50, and second time you add the mass 50 pound. This is 50 pound. When the 50 pound is added here in the second case, then the time period increase. So you will just change the mass will be changed, and by equating the equation, time period, both time periods are also given, mass is changed and mass is unknown, and you can then determine the value of the stiffness also for the table, because this is not different problem. For two equations you have to make and then try to solve this problem. I will also send the solution of this problem, because there are two equations are formed and you have to solve the problem. This is a spring mass system problem. A vibrating system consisting of a weight of 10 pound and a spring with stiffness K 20 pound per inch is viscously damped so that the ratio of the two consecutive amplitude is 1 to 0.85. Determine the natural frequency of the undamped system, logarithmic decrement, damping ratio, damping coefficient, and damped natural frequency. So in this system, W is omega is first is unknown natural frequency, you know, that is K over M, and stiffness is given K. So K over M, is also given because the weight is 10 pound. So M over G. So you have to divide the M as this M over G. So K over M is computed. From that the frequency can be commuted, and delta, you know that delta is equal to log of U1 over U2 is delta. So that can be computed, the ratio. From the ratio, the damping ratio can also be computed from the delta, because that is equal to delta over, you know that the delta is 2 pi into zeta. So zeta will be delta over 2 pi. So that is the damping ratio, and the critical damping ratio can be computed. Damping coefficient is zeta into CCR, and CCR, you know, is equal to zeta into uh, mm, that formula is used into K into M. So that is used K into M, and then you can compute the value of the C. And from that, the damped period of vibrations, natural period of vibration omega d, damped is omega into 1 minus zeta square. So omega is a natural and this is the damped. So damped period can be computed from this. You can also plot this response in the MATLAB. So now let's get an idea that, because this topic is also over the damped system, so how to plot the response in the MATLAB for this system. So in this, you can see that the if the same problem is solved in the MATLAB, you have the M value, K value, C value is present here, mass, stiffness, and damping, and then you can give the initial condition U naught and V naught. Screen is visible?
Yes, sir.
And then come the omega value, that is square root of k over m. Initially the condition u naught and v naught are given, because the problem is that the same example that we solved, plot the response with following damping ratio. This, the initial condition are the displacement of 1 inch and velocity of 0 inch per second. So v naught is 0 and u naught is 1 inch. Initial condition m, k and c are given. Omega is square root of k over m. So SQRT, the MATLAB function. So we compute the natural period and natural frequency. Next step is to compute the critical damping coefficient, that is CCR. So variable name is C underscore CR, that is equal to 2 square root K into M. So that is computed critical damping coefficient. Then the damping ratio psi is computed. Psi is equal to C divided by, this is backslash slash is divided by CCR. So C is computed, and from that C value you can compute the xi value, zeta value. Zeta is given because the problem is for different zeta. So first zeta is, this is made as a vector. First zeta, second one, third one and fourth one, damping ratios vector is formed. Now for this all value, for all zeta value, we want to compute the response. First zeta, so we run a loop for estimation for loop. For each damping ratio we are calculating. That's why for I is equal to, it means that the counter first value is 1 to 4, all 4's zeta value, this is computed. Now zeta I become variable, zeta become variable because these are the 4 different values. So omega d is computed, square root 1 minus zeta I. So every time one value is picked, when I is 1, so zeta first value is picked, when I is 2, zeta second value is picked, and omega d is computed also 4 times. Then you run the time interval 0 to 6 second with 0.01, and you compute the different value. The first value is the, this is the factor exponent raised to power minus zeta omega t. This is the exponent argument 1, and c is also computed, square root of v naught. This is the function that we proved for the, these are the equation that we proved for the undamped system. So you compute that argument 1 is also used in that function, and c, this is basically the amplitude exponent of zeta I omega into t. This is the argument 1 when it is multiplied with the c, square root of v naught plus u naught into zeta. So this equation is proved today for the damped undamped system, for the damped system, under damped system. And phi is the phase angle, that is the tangent inverse, and then you can use the v naught plus u naught zeta omega or omega d or v naught. So now we have the values of these. From that we can pick the maximum value, that is the amplitude, and you know that the amplitude multiplied by cosine of omega d t minus phi, this gives you the u value. So u is computed for all I values, because now what is the variable here? Omega d is also 4 values. That's why u will also get the multiple values of the u. And in addition, the u is computed for every value of the t, because t is also run multiple times. So t is also a vector, and for all value of omega, the u is computed, u become a matrix, because for 4 I values and for multiple t values, you will get the 4 different columns of the u. One column for the first value of the omega, first value of the omega d, next column for the next, and so on. And then when you plot it, the first u value, u column comma 1, and you plot the second one. Why we are plotting all the time? Because there were 4 omega t. So we plot this value and give the title and x and y label. And when you plot this, you will get the four results. When the zeta is 0.1, you will get this expression. When the zeta increases, the amplitude is reducing. When the zeta further increase, it become the overdamped system. So when the system is overdamped, then the results are, you see that there is no vibration, and when it is underdamped and lesser value of the zeta, the vibration is seen, but it is reducing. So this is the difference from the previous case when you study the undamped free vibration, and this is the case, the damped free vibrations. So you have the four different plots. So try also practicing with this thing for other problems and make a more program in MATLAB like that. Try to join the class in time because some of the student is joining the class now.
सर वो नेटवर्क का इशू था, लिंक ड्रॉप हो गया था अभी.
Okay. So now we were working on this thing, the MATLAB program. So try to work on this program. Then come the next problem. So this was done in the MATLAB. The mass is at rest, partially supported by a spring and partially by stops. In the position shown, the spring force is mg by 2. At time t is equal to 0, the stops are rotated and suddenly releasing the mass. Determine the motion of the mass. This is also a problem from the Chopra book. The spring force when it is at rest is already there. Already there is some force of mg by 2. There are stoppers, and when the stoppers are rotated so that the spring can move, suddenly the spring release. So additional force in the developed is in the spring is Ku. Determine the motion of the mass. So set up the equation of the motion. First of all, spring, because there is already force in the spring is mg. In addition, the force developed in the spring will be Ku. The mass will make a force equal to mu, and the total weight is basically downward mg. So you can write down this equation, the force, basically the spring force, and the total force mu is the mass into acceleration, and the spring force, that is Ku, and this is equal to mg by 2 because already the mg by 2 is present. So total net effective force can be written in this form: mg minus mg by 2. So mg is downward minus mg by 2. The left net force downward is equal to mg by 2, and Ku plus mu. This is the force. Now you know that in case of the free falling object system that is under the effect of free vibration, the equation that we proved last time is a cos omega t plus p sin omega t, and in addition the force which is already present was, response was mg by 2k. This was already present, and general solution of this equation is written as a cos omega t. We can apply the boundary condition at time 0. The initial displacement was 0 and velocity is 0. So we can determine the value of A as minus mg over 2k. And when we derivate it, we can determine the value of the B because B is equal to 0. When we derivate it, the answer becomes 0. So A and B are determined. Now putting the value of the A here, A value, A cos of omega t, and P is 0, and mg over 2k. We can have this function. So this is the function of this system. Function of a spring which is subjected to the force of mg by 2. So the problem was that it is at rest and it is supported by spring and partially by stops. In the position shown, the spring is mg by 2. So already it was having some force mg by 2. That's why this mg by 2k remains with it. And finally, this is the response of the system. Try practicing the other problems also. And in this way, this topic, we have discussed the different problems, different aspects, the application of this topic, and try working on it and understand and differentiate the functions from the free vibration for the damped system. Yes, do you have any question?